Hi, this is Gerhard Wieser from Frinx, and I'd like to introduce to you today the UniConfig framework. We've been hard at work over the last month, and we are super proud to share with you today what we have put together here. The UniConfig framework allows network operators to more efficiently manage network configurations through a unified OpenConfig-based interface. So no matter what specific vendor device they are working with, they're always using OpenConfig as a basis for their configuration. Let me start with the southbound layer. Southbound layer provides connectivity to the network devices either through netconf or SSH telnet for CLI devices. Next layer up, the unified layer, we unify those different mount points into one single mount point so that upper layer applications only have to deal with one single application type which speaks OpenConfig and looks exactly the same to the application, no matter if this is a Junos box, if this is an iOS Classic box, and so on. At the next layer, the UniConfig layer, we are dealing with the device configuration, and we have the capability to read that configuration, to write that configuration to one or more devices, to build diffs between intended configuration and actual configuration, and to manage snapshots for transactions, either on a per device level or on a whole network-wide level. Last but not least, we have service modules that sit on top of the UniConfig layer. Those service modules speak IETF data models on the northbound and translate those to device-specific models towards the UniConfig layer. Next, I would like to show you a demo. We have two iOS Classic routers here. These routers don't support any netconf or any programmatic interface, it's just CLI. And what we do here, what we're going to demonstrate is how we can take these configurations, convert them into OpenConfig through the UniConfig framework, and then play them back and convert them from OpenConfig back into the Cisco-specific CLI. All right, let's have a look. I have two iOS Classic routers here, and a BGP IPv4 peering session configured between the two of them. And what I'm going to show you today is we're going to extract that configuration into the UniConfig framework. We're going to convert it into OpenConfig, store a snapshot, look at diffs between intended and actual configuration, and then push it back into the routers. All right, let's get started. What we have to do first is we have to mount these two devices, which is what's already happened here. I've already done this before, and now they are connected to the UniConfig framework. Okay, so what we will do next is we will synchronize the device configuration with the operational data store in ODL. So we'll take the information from the device and push it into the operational data store to make sure we have the latest information from the device. We'll do that by issuing those commands. In the background, those are two REST commands that are pushed to the device, to ODL, and ODL goes and fetches the data from the devices. All right, so we have extracted the configuration out of the devices and pushed into the operational data store of UniConfig framework, and we now can have a look at the configuration. So what we see here is the whole router configuration converted, transformed into OpenConfig format. So we see everything from OSPF to BGP to interface configurations. Here's the OSPF statement. Here are the interface summaries. Here are the interface specific configurations, IP addresses on interfaces. So everything that you are familiar from OpenConfig is filled out with the information from the router. Again, this was taken from the CLI, it was converted into OpenConfig, and now that's the content of our config data store. All right, now as a next step, we're going to go to the devices and we're going to remove BGP. So no more BGP on the router. All right, no more BGP on the router. So now we're going to sync the devices again. That means we've changed the device configuration. We got to sync it back again with the operational data store. And then we compare the the config data store with the contents of the operational data store, with the current configuration of the devices. And we're going to look at the diffs. All right, here are the diffs. Shown in green is what's in the config data store, but what's not on the device. So we removed BGP, and here we see the complete BGP configuration in OpenConfig format that we removed on the device. Here we see the neighbor statements. Here we see the local aggregate, which is the network information, and so on. This is on both routers iOS 1 and iOS 02. Now, what we want to do, what we want to demonstrate here is how we can commit this diff to both devices. So create a network-wide transaction on both devices, only completed when both devices complete. And let's have a look how that looks like. Okay, we commit the UniConfig and we get back a complete from both devices. And let's see what's happening on our devices. We see there was some configuration action going on. And voila, BGP comes up again. Just to prove that we have actually configured BGP here, let me show you this little config statement. So this concludes the demo. Let me summarize again what we've done. We have configured a router with BGP, which is IPv4 BGP session, or 2 routers, and we've kind of synced those routers with the UniConfig framework. UniConfig framework transformed it into OpenConfig. Then we removed that BGP configuration on the routers, we synced again, and we had UniConfig compare the intent in OpenConfig format and the actual state in OpenConfig format. So we did a reconciliation, then we compared, and then finally we issued a commit statement, which means commit the intent into the devices, and after committing that, we've updated both devices and we've reestablished that BGP session with one command. All right, thanks very much. We'll share with you additional updates and more demos in the coming days and weeks. Take care. Bye.